Equilibrium, high level 1, equilibrium law. Essential idea. Many reactions are reversible. These reactions will reach a state of equilibrium when the rates of the forward and reverse reaction are equal. The position of equilibrium can be controlled by changing the conditions. Nature of science. Common language across different disciplines. The different dynamic equilibrium is used in other contexts, but not necessarily with a chemistry definition in mind. Employing quantitative reasoning. Experimentally determined rate expressions for forward and backward reactions can be deduced directly from the stoichiometric equations and Aristotelian principle. Theory of knowledge. The career of Fritz Haber coincided with the political upheavals of 2 world wars. He supervised the release of chlorine on the battlefield in World War I and worked on the production of explosives. It should make you think about how the social context of scientific work affects the methods of findings of science. And should scientists be held morally responsible for the applications of their discoveries? Okay, calculating equilibrium concentrations using ICE tables. Question 1. Given the equilibrium system, 2AB giving A2 and B2, if 5 moles of AB are placed in 10 decimeter cube sealed reaction vessel, an equilibrium is established where 2 moles of B2 are present. Find the equilibrium concentration of all reaction species. So using these ICE tables, we have the following information. We've got 5 moles of AB are placed at the beginning in a 10 decimeter cubed vessel, so we can put that in. 5 moles per decimeter cubed concentration. And at the beginning, obviously, we're going to have no A2 and no B2. We know that when equilibrium is established, equilibrium concentration of B2 is 2 moles, so we can put that in. And we know obviously it's in 10 decimeter cubed again. So what can we do next? Well, we know that the change in concentration is going to be plus 2, and changes always reflect the mole ratios in the equation. So if B2 is plus 0.2, then A2 will also be the same, and AB is going to be twice as much, because you can see the ratio. There's 2 here and there's only 1 there, so be twice as much, and obviously it's being used up, so it's going to be negative. So we're going to get minus 0.4. So we can then calculate the equilibrium concentration by having the initial concentration minus the change in concentration to give us the equilibrium concentration. And A2 will obviously be 0.2 as well. Question 2, 2x grams giving us y. We've got 8 times 10 to the minus 2 moles of x placed in the 200 centimeter cube sealed reaction vessel. So we can put that in straight away. 0.08 divided by 0.2 decimeter cubed to give us 0.4 moles per decimeter cubed. Obviously we have no y at the beginning. We can see that at equilibrium 60% of x is going to be converted to y. So we need to find what 60% of 0.4 is. You can actually do this just by multiplying by 0.6, and the change in concentration will be 0.24. And if we look at the molar ratios, we've got half the amount of this molar ratio, and so we'd multiply how much is used up by half, and we see how much of y, the concentration increase of y. Now we can take the initial concentration, subtract the change in concentration to give us the equilibrium concentration, and the concentration of y we've already calculated. Using equilibrium constants, we've got 5 moles each of A2 and B2, so let's put those in a 10 decimeter cubed reaction. So we've got moles per decimeter cubed. We're going to have no AB at the beginning. We're going to let x equals the change in A2. So we're going to have minus x at A2 minus x for B2, and this will be plus 2x, the molar ratios. So A2 will be 0.5 minus x, B2 will be 0.5 minus x, AB will be plus 2x. Right, so let's do the math here. We'll write out the equilibrium concentration. Put products on the top to the power of 2, because the coefficient was 2. plug in our x values for each one, and we've got 25 for the equilibrium constant. So we have take a root of both sides. It's going to give you the root of 25 is 5, the root of 2x to the power of 2 is just 2x, then you've got 0.5 minus x. You can take this 0.5 minus x over to the other side, so 0.5 minus 5 is 2.5, minus x times 5, minus 5x. Then you can take the 5x over this side to get 7x, 2.5, and 2.5 divided by 7 is 0.357. Now we can calculate the concentration of A2, which of course will be the same as B2 at equilibrium. So when we know it was 0.5 minus x from our ice table, so 0.5 minus 0.357 gives us 0.14 moles per decimeter cubed. And we're going to do the same thing for the concentration of AB, where we know it's 2x from our ice table, 2 times 0.357 gives us 0.71 moles per decimeter cubed. Let's have a look at this one. We've got an equilibrium constant, the initial concentrations. Initially we've got 0.6 moles of AB in 200 centimeter cubed. So 0.6 divided by 0.2 decimeter cubed is 3. Initial concentrations will be 0 and 0. We'll use x again for the change in A2. So that's going to be minus 2x because the coefficient up here is 2. And these two will be plus x. Oops. Better. So the equilibrium concentration for A2 will be plus x, B2 plus x, 3 minus 2x for AB. Write out your equilibrium constant equation. Make sure you get your coefficients correct. Plug in the details from the ice table and from the question. Square root both sides to get your x value. Then you can just use your information from the ice table to plug in your x value into here and calculate the concentrations. And that is the end of that presentation. Splendid.